Okay, it's time to start to put equations and numbers on the short circuit analysis. Okay, before I discuss the short circuit method, the method for short circuit calculation, I would like to introduce a few concepts, okay? I need that you understand many things about short circuit, and the first one that I need that you understand is that the short circuit is a dynamic behavior, okay? Later, I will use some assumptions, and I will simplify the problem, and I will use phasors to solve the short circuit calculations, okay? But at this moment, I need that you understand that the short circuit is a dynamic process inside the power system, okay? It's a very bad, abnormal process, but it's something that happened, and we need to understand how to deal with that, okay? What I will do now is I will use a very simple and very basic example and to show you the dynamic behavior of current inside the power system, okay? Uh, I am presenting over here a voltage source in series connected with a resistor and an inductor, okay? The supply is AC voltage. You can see over here is a beautiful sine wave with a frequency, okay, and a phase angle here, okay. However, probably you are wondering, okay, this is basic circuit analysis. Why do I need to learn this, okay? If you remember from your classes of electrical machines, the most basic model for a synchronous machine, without going in so many details about saturations and blah blah blah. What I need that you remember is that we can create a model that is an impedance behind a voltage source. An impedance behind a voltage source. If you imagine impedance behind a voltage source, when you close this circuit breaker here, this switch, what you are doing is creating a short circuit in terminals of this, let's say, circuit equivalent model for a synchronous generator. There is a reason that I start with basics with this RL series circuit, and then I will go to more complete concepts, okay? The first thing that you must understand is this is a sine wave excitation. That is what is creating troubles here. I don't know if you realize, but this phase angle here inside the sine, the phase angle have a very important factor, okay? Why? Because it's defining this point. For instance, if this angle is 0, at t equals 0, we close the circuit breaker and the instantaneous voltage at that moment is 0. That means that the voltage is at minimum. However, what's happening if we close that circuit breaker, but the phase angle inside the argument is pi divided by 2, 90 degrees? Well, the problem is that t equals 0, and this sign will be sine of pi half. And that means the maximum voltage deviation, that will be Vmax, okay? What I want that you understand is that in t equals 0, we close the circuit breaker, but there are possibilities that the instantaneous voltage could be 0 or even the maximum, okay? Now, if we close the circuit breaker over there, we can apply Kirchhoff voltage law to define the dynamic behavior, and we create this beautiful differential equation. This term here with the differential, the IDT, that represent the voltage drop across the inductor. Here we have Ohm's law applied to the resistor. This is the voltage drop across the resistor. And here we have the excitation, that is a beautiful sine wave, okay? This is a first order differential equation. A lot of you know how to solve this. I will not go in details. What I want to see, what I want to examine is the solution, okay? What I want that you understand is here the solution have mainly two components. One component where time is located here in this exponential, and the other one is the second component where the time is inside the sine wave, okay? In this expression, I try to put the expression in a way that resemble AC circuits. For instance, here in the denominator, we are using the magnitude of the impedance, and the angle in this case is coming from the impedance, okay? But coming back to my original discussion, I need that you understand that this expression for the current can be divided into different terms. One terms that we will call the AC or steady state or the alternating component, okay? And we say that because this term here, when times change, we are using a sine wave to define the changes on the voltage. On the other hand, we have the second component, we call that the DC component, and the DC component or transient component, or some books they call continuous component, is exponential that is trying to go to zero, and the time constant is related with the resistance and the inductance inside the circuit. Coming here, you can see there are two terms. Clearly, there are two terms. One that we call the steady state term coming from this sine wave, and the second one that we call the transient component, or that is coming from the exponential over here, okay? What I need now to make an assessment is what is the impact of having different voltages, instantaneous voltages when the circuit breaker is closed, okay? What's happened, for instance, if the switch is closed, but in this case, what you will realize is that the sine wave here, the sine is not zero. And as consequence, the sine is not zero, and we say there is a component, DC component, that must appear in order to keep the balance, because when you are closing the circuit breaker, you have a continuity. The current before closing the circuit breaker is zero, and immediately after we close the current will start to increase, but that current must come from zero again. What I'm trying to say is that this difference between angles phi and theta, they define the uh, mm, component, the DC component that is present in the current. Okay. Here in this plot, probably you can see much better. Okay. In red color, we have the full current. In red color, we have the full current. In this segment over here, you have the steady state component, or what we call the AC component, and this exponential over there that I am pointing out over there, that represent the DC component. When you combine the AC component, and that is the steady state component, with the DC component or the incremental component or transient component, many names, we will get this red, red wave over here. However, what is the important part of this? What I need that you understand is depending on the instantaneous voltage when you close the circuit breaker, you need to fulfill the requirement that the current must start from zero. I believe you can see that the DC component is positive, the AC component is negative. When you sum both of them, you will get zero. What I'm trying to say is the DC component is a consequence of the instantaneous voltage when you close the circuit breaker, that define the instantaneous AC component. What is the consequence of having a DC component? Well, the first thing is that the short circuit, that the current in the RL circuit will be non-symmetrical. I believe you can see at the very beginning, this is zero, and the current is not symmetrical respect to zero. And the most important consequence of having the DC component is the maximum value, the instantaneous value of the total circuit current. I believe you can see that the maximum value is increased by the DC component. Here right now you have two plots where you can see in this case they are not DC component and the current is totally symmetrical as the reference zero. But here we have the case that we have the maximum DC component. The maximum DC component happens when phi minus theta is equal to 90 degrees. At that time, when we close the circuit breaker, there is a maximum DC component, and as you can see here, the total circuit components create the maximum value. Okay? Okay, conclusion for this analysis. First, I believe you realize that if we have DC component, the instantaneous value, the maximum instantaneous value after closing the circuit breaker will depend of this DC component. Second, the DC component have an effect over the time, modifying the symmetry of this wave. Okay. Now, what is the situation? Well, I need that you understand that the situation in three-phase synchronous machine is very, very different compared with a RLSR circuit. I mean, why they are different? Okay, first, the analysis that we run before, it was a single voltage source, and when you are working with a three-phase synchronous machine, you have, of course, three voltages, and they are 120 degree between those voltages. Okay, that is the first point. And then, if you have a fault, you must realize that the instantaneous voltage at each line is different, and as a consequence, you will have DC component wherever you want it or not. And the second thing is that the dynamic behavior of a synchronous machine is not only an electrical behavior. They are also magnetic behavior related with the machine because the machine has a magnetic circuit. There are energies involved in that transient and the situation is a bit more complicated, okay? However, what I want that you understand is that um, I forgot to say here on the right hand side, you can see the plot, and that is the short circuit current. That is the short circuit current in a three-phase synchronous generator. Okay, you have the data over there. This is a Dixieland simulation. If you want to reproduce it, you can do it. But what I need that you understand is that the short circuit current over there, there is a DC component. You can see the oscillations and then damping over the time. Okay. At the very end, the short circuit current will be a sine wave, but you must understand that there is a transient over there on the current, okay? Now I will focus in the symmetrical short circuit current, okay? For instance, if I come back here, you can see that the phase B is totally symmetrical to the reference zero, okay? Now what I will do is I will stop in that uh, in that plot, and I will focus only on the symmetrical short circuit current. Okay. In this case, you can see that there is a component and there is an envelope. Okay. The envelope represents how the amplitude, the magnitude of this signal is reduced. Okay. I want that you understand the following. Here in the simulation, in the green line, we have just a signal, okay? This signal is the signal in green color over there that represent the current, okay? However, for practical analysis, electrical engineers, we realize that they are something very interesting. Um, when there is a short circuit in a synchronous machine, the current is modified because the energy involved in the magnetic field inside the machine. Okay, what I'm trying to say is in a resistor and inductor series circuit, the resistance is constant and also the inductance is constant. And of course, we are using an ideal voltage source and the amplitude of that voltage is constant, okay? The magnitude of that voltage is constant. However, in a synchronous machine, that is not the case because the internal voltage that is producing the short circuit current depend on the induction and the magnetic circuit properties. And on the other hand, the resistance will not change because that is the resistance coming from the copper wires. But the inductance inside the machine is coming from the magnetic fluxes inside the machine. When you have a short circuit in a three-phase synchronous machine, there is a massive change on the magnetic fluxes. As a consequence, the inductance cannot be constant over the time. Electrical engineers, we notice that and we decide, okay, the short circuit current can be divided in three different periods. One period that we call the subtraction period, one period that is after the first one and we call the transient period, and finally we have a period that we call the steady state, okay? This is for practicalities. This is in the order that electrical engineers, they can use some assumptions in order to make easy to calculate the short circuit currents, okay? What I'm trying to say is in real life, we have a continuous wave in blue color, but for practicalities, for short circuit analysis, we divide that blue signal in three different periods: subtransient, transient, and steady state, okay? Uh, and that is coming from something very interesting, that if we look here, the actual envelope, we can say that they are in reality, we can use mathematics and we say they are mainly three envelopes. One that is decreasing extremely fast from the very beginning, and we call that envelope the subtransient envelope. Then there is, after that, there is one that is decreasing, but not so fast, and that is what we call the transient envelope. And then there is an envelope that is not changing, and that is the steady state envelope. What I'm trying to explain to all of you is that this is the original situation, but we are doing an assumption. An assumption that here we have a fast decreasing, uh, fast changes on the magnetic fluxes inside the machine. There is a big current, and then there is a transition period, and then we have a steady state. We represent three different envelopes: subtransient, transient, and steady state envelope. And that is coming from a very simple fact. When the short circuit happens, we have the lowest inductive reactance inside the machine. That is what we call the subtransient inductive reactance. Okay. In red color, I am showing you a plot of the calculation of the inductive reactance of this machine. At the very beginning, we have a very small inductive reactance, and for a very short time period, this inductive reactance increases extremely fast, and we call that period subtransient period. And to represent that subtransient period, we can use an inductive reactance that we call subtransient inductive reactance. Then after that, the behavior of the total inductive reactance in the machine start to continue decreasing, but is slower compared with the first period. That decreasing is a bit, that increasing is a bit slower and longer, and that is what we call transient period. Okay, to represent that, we assume that in that period their inductive reactance is constant and receive the name transient inductive reactance. Okay, Finally, if the short circuit stay at the terminals of this synchronous machine, we have steady state faulty conditions, and we call that constant value, um, we call that the steady state inductive reactance for the synchronous machine. Okay? Okay, conclusion from this very important plot. The reactance inside the synchronous machine is only one. However, electrical engineers, we divide in three. That is the red color, I forgot to say. The inductive reactance inside the machine is only one and is plotted over there in red color. But for practicalities, in order to run fault analysis, we divide the inductive reactance in three periods, subtransient, transient, and steady state. And we assume that the reactance is constant inside that period, and you can see the lines in blue color, subtransient, transient, and steady state. Okay? Now, what I'm showing you over there is a set of equation, related to the um, analytical solution of the short circuit current inside a synchronous generator, okay, for a three-phase short circuit fault, okay. There is a DC component, that is what we call the transient component. There is an AC component, and you can see this is the sine wave over here. And finally, there is a double frequency component. I need that you understand there is a double frequency component in this real synchronous generator. And here you can see the double frequency argument inside the sine wave. I cover this topic about the double frequency signal on the synchronous generator for current in my classes of advanced power system, okay? However, at this moment, what you need to do is that component is damp extremely fast. As a consequence, typically not much people take in account that, okay? The next step is, okay, if we have three inductive reactants for the synchronous machine during a short circuit condition, well, we need to have three different models, okay? One model for the subtransient state, one model for the transient state, and finally, one model for the steady state. You are familiar with the model coming from the steady state. In that case, we are assuming that we are using a cylindrical rotor machine, no saturate, nominal conditions, etc. I will not go there, but over there you can see, you must be familiar with that model, and that is the steady state equivalent circuit. There are two more that we will be using. The transient state is not quite used for short circuit analysis, but is typically important for stability applications. Okay, we will discuss that in the next class about power system stability. Okay, what is extremely important is the subtransient state or period equivalent circuit, because that model is the model that we use for the short circuit analysis. Okay. Now, what I will do is I need to keep going with numbers on electrical power system analysis, specifically to short circuit analysis. Okay. When we are talking about symmetrical faults, three-phase short circuits, they are basically two different methods. The first thing that you must understand is, up to now, all the short circuit analysis was based on talking about a dynamic process. However, I don't know if you realize, but if you look carefully to those models over there, you must realize that I moved from differential equations to a very interesting and simplified concept, okay? If you are using the full differential equation, you will get the full picture about the short circuit, okay? You will get the beautiful wave that represents the short circuit. What is the problem? That in practical terms, that is not useful for short circuit analysis in big systems. We can do that using a software, for instance, using AMT simulations using the Excellent Power Factory, but it's not typical. Probably if you are working with new low carbon technologies, you are using power converters, probably you need to see see the full wave, the time domain representation of the short circuit current. But if you are working in a classical power system and you are working with protections or specifying devices and so on, you don't need the time domain representation. You don't need to see the full current waveform, okay? What you need to do is what we are doing now. I believe you can see over there those three circuits. And something that is extremely important is that you must realize that those circuits, quantities, you can see this is the terminal voltage, and I am using phasor representation in polar form for the terminal voltage. And in this case, I am assuming reference. That is the reason for 0 degree. And I don't know if you realize, but there is a beautiful J nearby to the inductive reactance, or they are subtracient inductive reactance. And that is because we are using phasors, okay? Now you are wondering, okay, what is happening now? Well, what I'm doing is I have, if you need to see the full short circuit current, use the time domain and use the differential equations. But that is not practical for the normal calculations that we run. What we do is typically use an approximation. The short circuit is divided in 3 periods: subtransient, transient, and steady state. And that is what we call quasi-steady state quantities. What I'm doing is dividing the short circuit in 3 different stages and 3 different periods, time periods. And in each one of them, I can use phasors because I assume that the inductive reactance of the synchronous machine is constant in that period, okay? That is the most simplified way that allow me this assumption allow me to use phasors and simplify the calculations, avoiding the differential equation, okay? From now on, I will be talking only about this situation, using quasi-steady state quantities, using phasors to represent voltages and currents, impedance to represent the resistance, reactance, and capacitance, and this is basically the tool that we use for short circuit analysis, okay? Now, there are two basic methods. Both of them, they are based on quasi-steady state quantities. One of them is the electromotive force, and I will tell you this method is probably one of my favorites because it's related with the load conditions inside the power system, provide probably the best or most realistic short circuit levels. However, it will take more time and require more data in order to perform calculations. On the other hand, Thevenin has been a very successful tool for circuit analysis. Now we can use Thevenin theorem to use for short circuit calculations, okay? Okay, let's start with the method that we call the EMF method, okay? Some of you probably will not find this method with a very specific name of EMF method in most of the books, okay? If you are a classicist like me, probably you will find some books that you can find the expression EMF methods. Some books, relative new books, like Stevenson, Glover, they use the expression internal voltage of a loaded machine under fault conditions, and they explain what I will explain in few seconds. Okay, this is just um, this is just a clarification, okay? People from the industry, people that probably have training and classes before Stevenson book, probably you will find another expressions, okay? Okay, let me start my explanation, okay? My explanation will start with, let's take a very basic power system, okay? This explanation is based in this specific power system here, because I want to show you a specific case, but then this method can be generalized, okay? Can be applied for many other conditions, okay? Let's assume that we have a synchronous generator here that is using a step-up transformer, and then this step-up transformer has in series a transmission line. We can say that is an external impedance and sending power to somewhere else, okay? Classical generator transformer line, okay? And for a situation, there is a moment that at point P, there is a three-phase fault, okay? Before my colleagues from the utilities and some colleagues from the academia start to say something, I will assume that the load that is connected at that bus bar is a static load. That means there is no dynamic related to that load, and we can assume that the simple model for that load is an impedance, okay? Later, if you have a dynamic load, like another synchronous generator, another or synchronous motor, or an induction motor, that is another history, okay? However, this procedure that I will explain here, it will be the same, okay? Okay, um, where to start? Very simple. We have two conditions over here. I believe it's clear to you that we have a pre-fault condition that this generator is supplying steady state supplying power to the load, okay? We can assume again that is a static load. We can use an impedance that is set load, okay? Now, suddenly we have the short circuit. The short circuit is happening here at the terminals of the load, a three-phase short circuit. We can say that the impedance is zero. That is what we call a volted three-phase short circuit, okay? During the short circuit, we have three different scenarios. We have at the very beginning the subtransient response, then we have the transient response, and finally we have the steady state, okay? For consideration from here and on, when I am studying when I study any kind of three-phase short circuit, I will be referring to the highest magnitude of short circuit currents that is happening during the subtransient period. Okay. Okay. Now, what is this? On the left-hand side, we have the equivalent circuit. We have the equivalent circuit for the conditions before the fault. And on the right-hand side, we have the condition during the fault, okay? Before the fault, I believe you realize that the model is extremely simple. Let me start from here. We have a static load. We use an impedance. This is the terminal voltage across the load before the fault. On the other side, we have a synchronous generator in series with a transformer, and then we have a transmission line. We can use the basic model for a steady state, a voltage in series with the reactance. And this is the circuit describing the load current before the fault, okay? Then we have a three-phase short circuit. The three-phase short circuit is very simple. It's a terminal condition where the voltage is equal zero at the fault location, okay? In this case, to represent 0 voltage, we put this ideal cable over here, and the short circuit current is moving on that cable, okay? During the fault conditions, remember something, I need to explain this for clarifying something. Those models, they represent line to neutral representation, okay? We are talking about symmetrical and balanced three-phase systems, and as a consequence, we can use the single-phase equivalent model to work quantities, okay? What I'm trying to say is this is the single-phase equivalent model before the fault, and this is the single-phase equivalent model during the fault, okay? Okay, here we insert this short circuit, but you must remember this short circuit is going to be a three-phase short circuit, okay? Okay, I believe all of you are familiar. Before the fault, we have here the steady state impedance coming from the generator in series with the external, in series with the load. Okay, there is a single current in this loop, and that is the load current. You can use Kirchhoff voltage law, and you can say the internal voltage of this generator is equal to the sum of voltage drop here, okay? That is the equation number 2. I believe from here you can realize the starting point for the name of this method. This method received the name EMF method, and the reason is because to calculate the short circuit currents, we are not doing that now, but this is just a short introduction. When you calculate the short circuit currents, you need the EMF, the internal voltage inside the rotating machine, okay? During the fault, we install here a short circuit, and during the short circuit, now the machine have here a remember that we are studying the subtransient period, and the subtransient period, the model is the subtransient voltage, but we are assuming that the voltage regulator of this machine is not acting, and as consequence, the internal voltage is the same during the short circuit. I mean, subtransient, transient, and steady state, they have the same internal voltage. However, the subtransient inductive reactance must be used in this machine, and here we have the circuit model for this condition. I believe all of you are familiar with using circuit analysis, okay? If the voltage in this terminal is 0, that means the voltage across this static load is 0, the load contribution is 0, okay? What I'm trying to say is if we have a short circuit, and the load is an impedance, of course, the voltage across the terminal is 0, and there is not short circuit contribution to the fault, okay? However, on the left-hand side, the full current contribution is coming from this side, coming from the internal voltage inside the machine, okay? You can use Kirchhoff voltage law, and from there, the short circuit current that is moving in this loop on the left-hand side is easily calculated by dividing the EMF, the internal voltage of the synchronous machine, and the series impedance uh, to the fault point. Okay? Here, there are two interesting things. The first thing is you must realize from the very beginning that the internal voltage of the synchronous machines, they are involved in the short circuit current, okay? Second, I say early today that the short circuit current is limited by the impedance between the sources and the fault point. And third, I say to you that the short circuit currents, typically they are extremely high. And they are extremely high because the denominator of this equation over here, the series impedance and the external impedance, they are very small. I mean, a transmission line, they have a very small resistance because we don't want watts wasted over there. we have a very small reactance. It's the same for the synchronous machine. And as a consequence, the voltage divided by this small resistance create a very big short circuit current. Okay? Okay, good. Now what we will do is something very simple. In this equation, we can write the voltage divided by the impedance. But the internal voltage, remember, during subtransient period is the same coming from the load conditions. We can put the equation number 2 inside this equation of the short circuit current, and voila, we have a short circuit expression that is the equation number 3. Okay? It's very important that you understand the following. Equation number 3 defines the short circuit current in that specific case. Okay? But what I need that you realize is, first, in order to get that expression, that equation number 3, you need the internal voltage of any rotating machine connected in the power system, directly connected to the power system. I mean, it's not only synchronous generator, it's also synchronous motor, it's also synchronous capacitors, it's also induction machines that they are directly connected to the grid, okay? That is the reason for this name, EMF, electromotive force of any rotating machine, okay? And to demonstrate my approach, equation number 3 is telling you, okay, in the denominator we have this small impedance that create high short circuit currents. But I believe equation 3 is clear to all of you that the load current is involved on the short circuit analysis, okay? Advantages of disadvantages. This method, as you can see, requires the conditions previous to the fault or before the fault. That is the first situation. You need to have a full picture or the whole data before the fault. Typically, a load flow can give you that data, okay? However, in terms of practicality, solving problems by hand is that that is a problem, okay? And the second thing is this will produce to you the most realistic results because it's taking account the low current. However, I believe some of my colleagues from the academia and some other colleagues from the utilities, they will say, okay, but the low current is extremely small compared with the short circuit current. And now I will say to them, depend of the short circuit current. Okay, here I don't want to be philosophical about short circuit currents, and also I don't want to antagonize or have a discussion with people from the industry. What I want is that we realize that the load current can be included inside the short circuit current, and depending of the conditions, there is an effect that can happen, okay? My job here is not teach you what to avoid. My job here is teach you what you need to take in account because sometimes that can happen, okay? Well, now I will talk about the second method that we use for short circuit calculations, that is the Thevenin method, okay? The Thevenin method is coming from the circuit analysis. Many of you or a lot of people, many people know about the Thevenin method, okay? To be honest, it's just a expanded version or generalized version of the Thevenin theorem. To be honest, many people, I will say probably 99% of people, they use the Thevenin method for short circuit calculations, okay? To illustrate the explanation, I will use the same power system that I used before. In this case here, we have a generator, synchronous generator connect to a step-up transformer. There is a series transmission line, then connected to a load. Uh, In this case, we are assuming that this is a static load, and the static load can be represented by a impedance, okay? In the Thevenin method, for explanation purposes, you can see here we have the conditions before the short circuit, and you can see there is a voltage here at the terminals of the bus bar of the load, or let's be honest, this is the voltage at the fault location previous to the fault, okay? This is BPF. BPF stands for voltage at the point P before the fault, okay? Well, there is a voltage over here, okay? Then during the fault, we have a three-phase short circuit. We can say that the three-phase short circuit is simulated by a cable over there, impedance 0, voltage 0, it's a terminal condition, it's a shunt condition, and that is the three-phase short circuit, okay? However, if we want to solve this problem using the Thevenin theorem, well, what we need to do is create a model, and it's the famous Thevenin model. And all of you must realize that the Thevenin model is extremely simple. A voltage source in series with an impedance. Thevenin voltage and Thevenin impedance. That is the name for those components over there, okay? Well, the first thing that you must realize, is that we can calculate the Thevenin model here. We can calculate the Thevenin model here basically in two steps. The first step is we can say that terminals A and B, they define the fault point. And they define the fault point, and during fault conditions, I will connect a load between A and B. Of course, the load is the short circuit. It's an ideal cable, an impedance 0. But again, what I want to define is terminals A and B represent the terminals of the fault, okay? Well, and the Thevenin model that we are looking for is between terminals A and B. I believe all of you must realize that if we remove the load, that is the condition before the fault. And what is the voltage when we remove the load from the circuit? Very simple, is VPF, the voltage previous to the fault at the point P. Then the next step is, okay, now what we need to do is calculating the Thevenin impedance. Well, the Thevenin impedance is extremely simple. The Thevenin impedance is calculated between A and B, terminals A and B. And I believe for all of you, it's very simple that we need to switch off this voltage source, and switching this voltage source and calculating the impedance, you can see those impedance on the left-hand side, they are in series connection and then connected in parallel with the load. There is a reason that the Thevenin impedance is calculated like the parallel between this impedance, the load impedance, and this series impedance between those, okay? Okay, but what is the interesting thing here? The interesting thing here is now to calculate the short circuit current, what I need to do is connect my load to the Thevenin model. Now the load is an ideal cable. The load is the short circuit. When I install the short circuit between A and B, we have current moving in this loop, and that is the short circuit current. And the short circuit current is easily calculated like the voltage divided by the impedance. That means that the short circuit current will be the voltage, the Thevenin voltage divided by the Thevenin impedance. Well, It's extremely simple to see that the Thevenin method is extremely simple, because the Thevenin method, you require the Thevenin voltage that, coming from the definition, is the voltage previous to the fault at the point of the fault. And then what you need to do is calculate the Thevenin impedance, and that is all. Okay? Typically, people using short circuit analysis based on Thevenin method, we can assume that the system is working at nominal conditions, rate conditions, and we can assume that the system is unloaded, for instance. And if that is the condition, that there are not low currents, that means that all the voltages inside the power system, they have the same value in per unit if the bases are properly calculated. But coming back, all the voltages will be 1 per unit, and it will be simple to define the short circuit current as the ratio between 1 per unit and the short circuit impedance, that is the Thevenin impedance. Why people like so much Thevenin method? Well, because the Thevenin method is very simple. If you know the voltage at the point of that the fault happened, you just need the Thevenin impedance. And there are many mechanisms. You are a top expert in circuit analysis. There are many methods that you can obtain the Thevenin impedance, okay? Especially if you took a training about or classes about using matrix method for solving power systems, okay? Um, okay. Um, now what I will do is I want to show you the generalization or demonstration of the Thevenin method, okay? To do so, what you need to understand is the following. The Thevenin method, the general Thevenin method for short circuit analysis, is coming from superposition. I mean, all the circuit or the circuit analysis methods, they can be used inside the power system, okay? And if you remember, we are still using the same power system. And okay, this power system will be used to show you how to understand the Thevenin method based on superpositions, okay? What I will do now is I will take the equivalent circuit of this power system, considering uh, conditions before the fault and during the fault, okay? And if you look, okay, what I was explaining here is that this switch, when the switch is open, we have the situation before the short circuit. When we close the switch, we have the short circuit current moving across the switch, okay? From the practical point of view, the switch open means before, and what I need to know is there is a voltage across the terminals of this switch, and that is the voltage before the fault, VPF. When I close the switch, now the voltage is 0 because we are simulating the short circuit, okay? From the circuit point of view, you can see the two circuits here below. If we have the switch open, we have a voltage source over there, and we can say that this voltage source is the same voltage before the fault. From circuit theory, you must know that if we install that voltage source over there, there is no current going over there because the voltage source has a voltage equal to the voltage that is located over there. I mean, it's like connecting something in parallel with the same voltage, no current will go through, okay? But on the other hand, wow, we can use something very clever. What we are doing is, okay, on the top, you can see that when we close the switch, there are short circuit current over there because the voltage across the terminals is 0. But what if we do something very clever? We connect over there to voltage source, one with the positive polarity to the top and the other one with the positive polarity going to ground, okay? What is happening is that you have the same voltage but with two different polarities, and when you apply Kirchhoff voltage law over there, voila, the beautiful mathematical trick. Here you can see that the voltage, the equivalent voltage between A and B is zero. That is pure circuit analysis, pure Kirchhoff voltage law, but it's beautiful and clever. Why? Because coming back to my situations, the original circuit for short circuit conditions, the original circuit for short circuit condition is the we have the switch closed and we are simulating the voltage zero across the terminal of that switch, including two voltage sources with opposite polarities. That is this situation. How many voltage sources do we have over there? We have three different voltage sources. We have the voltage source that is coming from the internal voltage of the generator. Here we have one voltage source and one more voltage source. That means based on circuit theory, I can use at maximum 3 superpositions. However, in this stage, I will be clever and I will use only 2 superpositions, okay? Why? Because I have 3 different voltage sources. I will switch off one and keep running 2, and then the superposition 2, I switch off the previous 2 and keep running the third, okay? Superposition 1 is basically what we are doing is keeping on the generator and this voltage source over here, that is the voltage source that is having positive polarity and the same voltage previous to the fault. That means that the current that is moving here is zero. And that is beautiful because the second superposition, I switch off this voltage source, I switch off that voltage source, and now we have the voltage source with the positive polarity going to ground. And that is a situation that we can see that there is some current going through this voltage source, okay? Superposition 1 is extremely simple. Superposition 1, the current going inside this voltage source is zero, but all the load current starting from here is going to there. That means that the short circuit contribution during the fault is zero. On the other hand, during superposition 2, I have this voltage source and there is current moving in this branch and there is current moving in this branch, and both of them are going to the short circuit. For circuit analysis, you can use the circuit analysis that you want, but the fault current will be this voltage over here, this beautiful voltage divided by the total impedance. And what is the beautiful surprise? That the total impedance is equivalent to the Thevenin impedance that we already calculated. What I'm trying to say is the impedance between A and B is the load impedance in parallel with this series of the branch on the right hand side. What is the consequence? Well, the consequence is extremely simple. The consequence is that using superposition, we obtain the full demonstration of the Thevenin method. The Thevenin method say that the short circuit current will be Thevenin voltage divided by the Thevenin impedance. The Thevenin voltage is coming from the voltage at the fault point previous to the fault. And the Thevenin impedance, well, in a basic circuit, you can use basic circuit analysis, series and parallel, or even in a bigger power system, you can use delta and star transformations, or even if you have a beautiful, very large power system, you can use matrices, impedance matrix and admittance matrix. Well, what I will talk right now is when there is a fault inside the power system, there are some devices that they allow the production of short circuit currents. What I'm trying to say is imagine that we have a power system, okay? In this case, I am using an industrial power system because it's probably the best way that I can show you all the sources of short circuit current, okay? Imagine that we have here, this is the power supply coming to your industry, and inside you have a cell, and that is the substation. There is a local generator, synchronous generator. There is a local synchronous motor, and there is some induction motor, and there is a fault here. The fault happening is a three-phase short circuit fault. Okay. The first thing that you need to realize is when there is a short circuit inside a power system, any AC rotating machine directly connected to the grid will provide or will contribute with current to the fault. I will say again, when there is a short circuit inside your power system, and I am not talking about three phase, I am talking about any kind of short circuit fault. When you have a short circuit inside your power system, all the rotating machines directly connected to the power system, they will produce current that it will be add to the short circuit current. It will be a contribution to the fault. Okay. What are the main sources of short circuit current? Okay, any synchronous generator, any synchronous motor. It could be synchronous motor or it could be also synchronous capacitor. Induction motors, okay, directly connected to the grid. If you have a converter, a variable frequency converter, no. That is another history and it's beyond this basic class about short circuit, okay? And the other component is the supply coming from the utility. Here, this is a very famous slide that is coming from, if my mind is properly correct, I think it's coming from Beeman, the book of Beeman. However, what I am showing over there is the plot of the, let's say this is an approximate plot of the short circuit contributions. Okay. The source coming from the power supply is probably a very big and non-decreasing short circuit currents. Local generators, they provide short circuit contribution, but is damped over the time. Synchronous motors, they are similar to synchronous machines. They provide short circuit contribution, but is damped over the time. Okay. The induction motors. They provide short circuit contribution. Okay. The contribution will depend on several factors. One of them depends on the size of the induction motor. Some standards say that motors below 50 HP horsepower, they are not providing contribution. They can be neglected. However, that is talking about the case of standardized short circuits. That is not my subject today. Okay. And finally, here we have a plot that is representing the equivalent short circuit current inside this system. Okay. Power systems are very large networks. okay? When you are calculating short circuits at real power systems, you need to have a full understanding about the short circuits at almost every single bus bar. If you are using Thevenin method and you are trying to use parallel and series reduction, step-by-step reduction using delta stars and so on, that could take ages. Yeah, that could be time consuming and that is not efficient. Some of you already took classes about power flow, and some of you have already taken classes about matrix methods applied for power systems. Okay, um, there is several good explanation in many books. Um, for instance, chapter number 6 of Stevenson book, you can find the full description about the network calculations, nodal analysis, and then the impedance matrix and the Thevenin methods and so on. Okay. I will not go into the details about how to create the admittance matrix or how to create the impedance matrix. Okay, my job here is going into the details of the short circuit analysis using um, short circuit analysis in large networks using the impedance matrix. Okay. Well, as we discussed before, Thevenin method and EMF method are used for short circuit analysis. EMF method require the full understanding, sorry, the full understanding and details of the pre-fault conditions, and that is coming from the load flow. Okay. And Thevenin method by hand can be used for medium-sized problems. But if you need to calculate short circuit currents using a very big network, a large network, you need to use matrices. Okay. Again, it's not my job here to discuss about the method, but what we need to do is understand how to use those matrices. Okay, the first thing that you must understand is that for those calculations, usually we can neglect the load currents. That is what is making easy the calculations. Okay. Some other ways is that you can include the load conditions inside the matrices by including the effect on the voltages, but that is another history. Okay. What I will do is that for a very large electrical power system, what we need to do is using impedance matrix because it's the most effective method to cope with the short circuit analysis. Okay. The impedance matrix is a very simple matrix. It's a square matrix, and that square matrix is coming basically from the application of the Kirchhoff voltage law. Okay. Set here represent this matrix, that is the impedance matrix. I represent here the current vector, and V represent the voltages. Okay. And what we want to do is, well, how do we use this for short circuit analysis? Okay. The generic explanation using the full matrix, it could be a bit abstract. For that reason, what I will do is consider a very basic power system. Okay. I believe you can see there are four bus bars here. There are three generators. There are three step-up transformers. Okay. On the right hand side, what I am presenting is the reactance diagram during the fault conditions. Okay. The fault is a three-phase fault. Apply here at point P, and you can see that we can use the beautiful mathematic trick. There are two voltage sources over there, one positive, one negative. The total voltage across the terminals is 0. That represents the short circuit, okay? I believe all of you must remember that this is the situation. This is the situation where one voltage source represents the voltage previous to the fault at the fault point, and the fault condition is represented finally, or the short circuit currents are created by this voltage source over there. Okay. Well, what we need to do is, okay, now, how do we calculate these fault currents based on those circuits? Okay, if we assume that the fault is happening here at bus bar number 2, we can identify that the voltages created during the fault condition, the voltages created during the voltage condition, they are defined by this 4x4 matrix, and that is the impedance matrix. Okay? And what you need to understand is during the fault conditions, the terminal voltage at bus bar number 2 is 0. Again, I will tell you again, during the short circuit conditions, the voltage at bus bar, the faulty bar, is 0. However, if you look over here, the voltage and current relationship, I am using delta V1, delta V3, delta V4, okay? Delta V1, delta V3, delta V4. And here for the bus bar, there is a minus voltage at the fault point. What is the reason for that? Well, considering the fault at bus bar number 2 and considering just the voltage source that is exciting the short circuits, that means that we are creating is a differential voltage in every single bus bar. What I'm trying to say is those terms over here, delta V1, delta V3, delta V4, what they are doing is they represent the change of the voltages during the fault condition. I mean, those delta V represent the voltage previous to the fault minus the real voltage at the bus bar. For instance, bus bar number 2, if you can see over here, the second position is minus BPF. What is the reason? Well, because during a fault in the bus bar number 2, well, I have been explaining that impedance matrix is extremely powerful, and also especially for calculating electrical variables inside large power system. However, one of the difficulties, one of the problems one of the issues related with using the impedance matrix is that the matrix is a abstraction of the real power system. Okay, you must understand that it's an abstraction. Physical connection between the understanding of the one element inside the matrix and the real physical component is a bit difficult to do. Okay, in reality, the topology of the power system is included inside the impedance, but it's not straightforward to see that connectivity inside the matrix. Okay, however, what I want to do is I would like to show you. There are many books that they present equivalent circuit that is created for the elements relating the elements of the impedance matrix. Okay, here I would like to show you this this network is presented in few books, especially, for instance, in Stevenson. Um, mm, some people ask me, what is better, understanding the equations that you present before, or fully understanding this model that you will show? My preferences is because I am a programmer. I prefer to understand fully the equations and understand how to use the equations instead of creating the circuits. But some students, they prefer to have a grasp, sorry, to the circuits, and that is the reason that I am presenting here. Okay, what you need to understand is if you have a bus bar that it's supposed to be faulted, and that is the bus bar K. What you need to do is represent the elements that they are connecting inside the matrix, that they are relating the bus bar K and the bus bar J, okay? Uh, the elements that you will put here in series with the voltage source is coming from the element Kj or Gk, because remember the impedance matrix is symmetrical, and as a consequence you can use any one of them, okay? Let me examine this loop over here. If you look this loop over here, what you can see is you have this impedance in series with this impedance when this switch is closed, okay? But if you use basic mathematics, you have here, let me use the other pointer here. If you look over here in this loop, okay, in this loop, you have this impedance over here in series with this impedance. That means that the fault current should be this voltage divided by the total impedance. But you have one here negative, you have here one positive, and as consequence, you get the same expression that I was discussing before. That means that you can calculate the short circuit current at any bus bar, the bus bar K, by dividing the voltage previous to the fault at the fault location, and by the impedance, the elements inside the impedance matrix representing the position KK. Okay, that is what we call the self-impedance element of bus bar K. Okay, and if you are interested in voltages, you can do something similar. But now what you need to take in account, is the voltage in bus bar J. And what you need to do is, okay, how much is the voltage here between this and reference? Okay, you must realize that this bus bar here is doing nothing because there is no current in that bus bar. And as consequence, you can say that the voltage here, Vj, is equal to the sum of the voltage here plus, remember, this is negative, this is positive, that is the reason for the negative sign over there. And you can say that the voltage Vj here will be the BPF, voltage previous to the fault at the point P, minus this element multiplied by the fault current, okay? Then you include the definition here, and you will get the expression that I already did. Something that is interesting. This circuit is coming from the equations that I showed before. I mean, the history is not otherwise. On the other direction. The history here is this circuit model is created based on the equations that, using pure and beautiful mathematics, I got for you. Okay. Again, I am just presenting this because some books they include this. I am a programmer. To be honest, I don't need the circuit representation. To be honest, the circuit representation is a bit messy for me. However, if you have a full understanding and if you have the full command of those equations, that is what is relevant for us. Okay. Okay, now my students, they are top experts on short circuit analysis, okay? They have the possibility of calculating the symmetrical short circuit currents using Thevenin, using EMF method, or even using the impedance matrix for a very big power system. Now, the interesting question is probably you are wondering, okay, now I got the symmetrical short circuit current. Where do I use the symmetrical short circuit current? Okay, before I start this explanation, I know that many of my colleagues coming from the consultancy, that they are designing substation, they are specifying bus bars, they are making calculation for grounding grids and so on. Please, this section is for students. This section is just to try to understand the basic concepts, okay? This is not a video for consultants or for people that they are doing jobs inside specific cases, okay? What I want to clarify here is that here we are presenting the basics, okay? The basic use of the symmetrical short circuit currents, but then when you are in the field, they are very specific. They are very specific cases. They are standards, and also they are documents coming from the manufacturers that they will specify calculation methods and uses of those numbers for specifying components. Okay. What you need to understand is that the short circuit current is used for many things. It's used for many things. For instance, is the input for other studies. If you are taking my classes of power system protection, you must realize that if you are calculating or settings of a current relay, you need to know the short circuit level, maximum short circuit level, minimum short circuit levels. Okay, that is one use of the short circuit currents. But there are many. Grounding systems, power quality, safety, arc flash, and many other areas, okay? Here in this class, I will try to make my best in order to show you a very basic introduction of the selection of circuit breaker, power circuit breakers, okay? The first thing that you need to understand is when you are calculating short circuit levels, for instance, if you are working in a refinery inside the oil company, and if you need to install a new motor and you need to select the circuit breaker for that new motor, you need to calculate the short circuits. And the refinery probably it's connected to the power grid. And what you need to understand is that you need to know what is the Thevenin equivalent model from the utility. The utility will not give you the Thevenin impedance. Instead, when we are working in the power utilities, what we will give you is basically the short circuit capacity. I mean, at the bus bar that you are connected, the power utility will give you some MVA, that is capacity, apparent power, and those MVA represent the short circuit capacity of the bus bar that you are connecting. Now, the question is, okay, MVA. This is the equation over here. And because we are working with symmetrical short circuit currents, we are working with three-phase short circuit currents. For that reason, the apparent power that you will receive from the power utility, in this case, this is a three-phase short circuit current, okay? Later in my class about asymmetrical faults, we will say that they are another capacity for single phase, for single line and for double line faults, okay? But in this case, we have a square root 3 nominal voltage, and we multiply by the magnitude of the short circuit currents. And what we get here is the customers or the megavolt amperes that represent the short circuit conditions. And from there, you can use this number to calculate your your Thevenin equivalent model. And it's very simple, because if you consider that the utility is giving you those megavolt amperes short circuit capacity, well, you can use those as base power, and you can assume that we are using the rate voltage as a base. And what is the interesting thing? Well, the interesting thing is that the short circuit in per unit is numerically equal to the capacity in per unit. And from there, it's extremely simple to say, that we can create a Thevenin model. This voltage is the Thevenin voltage. We can say that this is 1 per unit because it's the rate voltage. And the short circuit current will be numerically equal in per unit system to the MVA short circuit levels in per unit. And it's very simple to say that the Thevenin impedance is 1 per unit divided by the short circuit current, but the short circuit current is numerically equal to the apparent power, and from there we can obtain the Thevenin impedance. It's beautiful. The short circuit capacity, the MVA of short circuits, can be used to create the Thevenin equivalent model of a system. Okay, but this Thevenin model is for short circuit for calculations. Okay, now I would like to go more into the selection of circuit breakers. Okay, the first thing that you must understand that the circuit breaker is a mechanical device. Well, to be honest, it's an electromechanical device because it's using mechanical forces to try to stop and interrupt fault currents, and that is electricity, okay? The circuit breaker is trying to stop the short circuit current, opening the contacts, okay? For that reason, the circuit breaker have a very important mission, and that is try to extinguish, well, it's not try, it must extinguish the arc that is created during the fault, and to do so is doing two important things. One, increasing the length of the arc, that is what we call elongating the arc, and the other thing is cooling down the arc, and that will allow you in one of the crosses by zero, you can stop the short circuit current. Okay. Mainly, that is the basic functionality. That is the basic way that one circuit breaker is operating. I know that there are people only specialized on circuit breakers. They can go more details, but this is the basic things that you need at the moment. Okay. What I want that you understand is that circuit breakers can be classified in many ways. However, it's important that you understand that low voltage circuit breakers, they are very different to high voltage circuit breakers. And we say here low voltage circuit breakers is everything below 1500 volts. That is what the standards say. And if you go above is 1500, okay? Especially I will be dealing with high voltage circuit breakers, and I say early before that we need to extinguish the arc, and there are different mechanisms, different elements that we can use to cool down and to try to break the arc. For instance, very old brake, they use air, then we start to use oil, but this is a insulating oil, okay? Then we start to use very interesting chemical scenes like SF6, that is a gas, and also very old and sometimes still in use, the vacuum, okay? However, I need that you understand there are different technologies for circuit breakers. Depending of the voltage level, the construction is different, and also depending of the mechanism using to cool down and extinguish the arc, there is a classification, okay? Okay. Now I must keep going honest with my students. The selection of circuit breaker is a very delicate job. However, in this module, what we are trying to do is make an introduction, make my student familiarize, be able to calculate and specify generic circuit breakers. Okay. In reality, this presentation is not dedicated a full study of a circuit breaker applications. Okay. Selecting a circuit breaker starting with voltage levels, insulation level, frequency, and there are many other mechanical and even civil engineering related aspects. Okay, I will not cover this. This presentation is only to show you the importance of understanding how you connect the full level calculations with the specification of circuit breakers. Okay, a full guide on how to specify circuit breakers can be found mainly on standards, but the standards, they are generic. And what I suggest is if you are working in a ultra high voltage or extra high voltage circuit breaker, go for the original manufacturer equipment documentation. There are more data over there. Okay. I need that you understand that they are basically any circuit breaker. They are basically two important factors that you need to take in account. There is a maximum current that can go through the circuit breaker. If you remember, there is a DC component inside the short circuit currents that make that the instantaneous value of the current can be high. And during the first half cycle, you will have a very big current. That is what we call the maximum instantaneous current. Okay, the device, the circuit breaker, all the components must be able to allow this current passing through. Okay, it must be able to support to withstand that current. But then there is a protection relay. They will take some time to operate. They will send the signal to the breaker, and the breaker must open the contacts. Okay. As you can see, there are some time involved in this action, and this time is mainly related with the operating time of the relay, that today with the use of the modern digital technology, that time is extremely small. And then we have to stop the fault current, and that is the job of this circuit breaker. Okay, and when we receive the signal of stopping the fault current from the relay, that is where the breakers start to open the contacts. Okay, that is the current that we need to stop. That is what we call the total current or interrupting current. That is the current that when the breaker must cut down and break the arc, that is the current that we need to stop. Okay. Over here, we use the name interrupting rating. Interrupting rating is the name for specifying in kVA or MVA the capacity, the short circuit capacity that we need to stop. For instance, it's typical that for a circuit breaker, we say that the interrupting capacity will be, because we are working with three-phase current, is square root 3 multiplied by the voltage multiplied by the interrupting current. And the interrupting current is what I care about, because the interrupting current is the current that is lower because it's several cycles after the starting point of the short circuit, and the DC component start to decrease, has been decreasing, and the interrupting current will be lower than the momentary or instantaneous current. Okay, circuit breakers, they are different speeds. Okay, the speed on operating a circuit breaker depend on many factors. They are beyond my discussion here, but we say that the speed is explained in cycles. Okay, cycles, and those cycles refer to the nominal frequency. Okay. Okay. What you need to understand is that breakers, we need to define the instantaneous, that is the Winston of the circuit breaker, and then we need to define the interrupting current, but the interrupting current depend on the interrupting time. And the interrupting time depend on the technology related with the circuit breaker. Why there is a difference between the instantaneous and the interrupting current, or the momentary current and the interrupting current? Because the asymmetrical component coming from the DC component of the short circuit currents is changing over the time, and is supposed that is reducing the current. Okay. A small detail about the operating time. The operating time is quite interesting, okay? I highly suggest that you have a reading on the IEEE standard C37.09. That is the standard definition for AC high voltage air switches. And I highly suggest that you understand that the interrupting time of a circuit breaker is the maximum time that the circuit breaker can be energized and keep working, and then the contacts will start to open. Okay, that is mainly the interrupting time. The interrupting time have mainly two components. Okay, one, that the contacts start to separate, and that there is a arc that is created between the contacts, the fixed contact and the moving contacts, and this arc start to be long, long, and long, and start to be cooled down by the mechanism, for instance, vacuum, air, or SFCs. And then the arc start to be elongated and be cut down, and then the arc is extinguished. When the arc when the extinction of the arc on the primary contacts happen, when the extinction of the arc at the primary contacts happen, that is what we can say, okay, we have uh, successfully stopped the fault current, and now the circuit breaker is open. What I'm trying to say is there is a short circuit, then the relays and other devices take time, send the signal, and the breaker start to open the contacts. Okay, that is no instantaneous. But at the moment that the contacts open, there is an arc, and that arc start to be long and longer and longer, and finally we reach the point that the arc is stopped, the fault current is stopped, and that is the operating time. Okay. Okay, more definitions. You can go again to the standard, the C37.06. Please have a look over there, and you will see the full explanation and some tables indicating the classical or the standardized circuit breaker ratings for interrupting times. Okay. Okay. Uh, Now it's very important that we define what is the maximum symmetrical interrupting capacity. Okay. What I am showing here is based on the standard C37 from the IEEE and C37. Okay. There is a factor that is called the rate voltage range factor. What is the rate voltage range factor K? Well, is the division between the maximum voltage that you can allow in your circuit breaker divided by the lower limit of the operating voltage of your circuit breaker. Okay? What I'm trying to say is when there is a short circuit, there is a maximum voltage and there is a minimum voltage. The maximum voltage is typically defined by the insulation level of your insulation related in the circuit breaker. But the low operating voltage defined in some sense, I will not go in full details, but in some sense define the capability of your circuit breaker to still operating. Okay? Now, what you need to understand is that this factor is basically what defines the maximum symmetrical interrupting capacity. Okay, modern breakers, K, that is the rate maximum, the rate voltage range factor is typically 1. Okay, that means that these devices between the maximum voltage and the minimum voltage, there is no difference, almost zero, and that is the reason that the division is 1. Okay, but very old breakers, the history is different. Very old breakers, especially in great volume of oil, they have a key factor, a rate voltage range factor that is a bit higher than 1. Okay. Okay, and what that means is that for the same short circuit current, you will have more capacity of interrupting short circuit faults. Okay. Okay, one more thing before we move forward and finish this explanation. Um, I didn't formally introduce, but the short circuit that I am presenting here in my classes is what we call the complete method. The complete method is the method based on the impedances, real impedances in the system, and they are not multiplier, they are not modifiers, okay? However, many years ago, manufacturers, especially circuit breaker manufacturers, they must define the capacity of the equipment and they start to have different specifications. Years later, standards appear, and those standards try to create a law, not a law, a standard that allow the manufacturer to follow the same specifications, and utilities will have no problem buying one equipment or buying another equipment because all of them will be based on the same ratings, on the same standardized characteristics. Well, many years ago, ANSI started to create the standards C37 and C57. They are used for the short circuit calculations, simplify short circuit calculations in the US. Here in Europe, also we have the standard IEC 60909, and that is the short circuit calculations, simplified calculations based on the IC. Okay, that is the standard that tells you how to perform calculations. Okay, short circuit calculations. However, what is the problem? Those standardized methods, they have some coefficients, they have some multipliers, and depending of the conditions, they simplify, considering this or neglecting that. Okay. We will not cover that, but I will just show you a short introduction that ANSI have one simplified method that is called the EZ or EX method. Okay. It's basically a method that allows you to simplify the calculations by making some assumptions and using some multipliers. Okay. For instance, if you are using synchronous generators, well, you will use the full subtracient reactance for your short circuit calculations. But if you are using synchronous motors and you want to calculate the interrupting current, What you need to do is multiply 1.5, and that will be the approximate value for the transient reactance, and you can use the transient reactance to calculate the interrupting short circuits. What I'm trying to say is this simplified method is used to calculate the interrupting current. This method will allow you to calculate the interrupting current, but you need to use some multipliers on the reactance in order to get the approximation, how the reactance change from the subtransient period to the transient period. In this case, synchronous motors, you will multiply 1.5 the subtransient and you get the transient reactance. For induction motors, what you need to understand is that every single motor below 50 horsepower, individual horsepowers, you will neglect the contribution, okay? And depending of the size of a cluster of those motors, you can go to the ANSI standard and you will find some indicators, okay? Okay, but at the end, what you need to understand is that using those methods, you will calculate the transient inductive reactance, and then you will use to calculate the short circuit current. But this short circuit current, symmetrical short circuit current, will be the interrupting short circuit current. And then when you have this number, what you need to do is specify the momentary interrupting current, the interrupting current by using the relationship between reactance and resistance at the fault point, okay? If you know the resistance and reactance at the fault point, and this number is below 50, you can use the full current to calculate the capacity. If you don't know the relationship between reactance and resistance, okay, what you need to do is saying that you allow 80% of the value for the short circuit current to be used to specify, okay? Any more details, please, you can go to the ANSI C37.10 and see more details over there, okay? Probably you are wondering, okay, why this gentleman here care about this simplified method? Because in real life, you want to know what is the real current at the moment that you are interrupting the short circuit fault. What is the real current at the moment that the contacts of your circuit breaker is interrupting the current, okay? This is one way to do it. If you have time, if you have all the details, you can use this simplified method. And there are other methods, okay? For instance, uh, those methods, what they do is you don't recalculate the short circuit current for the for the moment that you are interrupting the current. This method, what you do is, okay, when you use EMF or Thevenin methods, you are calculating the subtransient current, and that is the initial symmetrical current, okay? However, that current not necessarily include the DC component. What you can do is doing something very simple. If you don't include the DC component and you obtain the short circuit current using the Thevenin method, for instance, and it's simple to demonstrate that the expression for the short circuit current will be something like that. You can use a mathematic trick and convert the short circuit current from this expression, voltage divided by impedance, into this expression. But probably you are wondering why I interested on the expression below. If the expression below look a bit more complicated. Well, from the previous slide, you must remember that the ratio between reactance and resistance, they have a strong impact on the short circuit because that ratio, reactance and resistance, that define how fast the DC component it will extinguish. And that expression inside the red box over there allow me to isolate two interesting terms. I think you can see that the interesting point here is that you can divide this into interesting areas. You can say that the marks that I put over there, to be honest, that is the calculation, the short circuit calculation, the short circuit current calculation without considering the DC component. That is true. And here inside this square root, you have a term that is defining the ratio between resistance and reactance. That is what is affecting the DC component. And that is what I am explaining here. What I am explaining here is that now we can obtain the full short circuit current, including the DC component, by using an approximation where we calculate the short circuit without the resistance. That is extremely simple, very easy to calculate the short circuit current. And this approximation then we modify considering this term in the denominator, and that term in the denominator will allow me to correct my simplified calculation and make resemble the real asymmetrical short circuit current. Okay, let me clean here for a minute. Okay, now this factor in the denominator is what is including, what is explaining the effect on the ratio between reactance and resistance. And to be honest, that is a very important term because in real life, this term, the ratio between inductive reactance and resistance, they define many important things. For instance, in classical power system, the resistance is very low compared with the reactance. And for that reason, the ratio between H and R is bigger than 4. And for that kind of cases, it's very simple to neglect the resistance. But if you are working at distribution level, the history is totally different. In distribution level, especially industrial levels, you have a resistance that is almost compatible with the reactance. And as consequence, you need to be careful, okay? Now, why I am explaining this? Because we can calculate the asymmetrical current, the asymmetrical short circuit current, using, again, the interruption and the momentary regime using the factor that I presented before. I say that the effective current, short circuit current, has two components, DC component and AC component. And using the same mathematical trick, I can say that the total fundamental and efficient short circuit current, it could be the AC current multiplied by this factor over here. This factor over here is what we call the asymmetry factor. The asymmetry factor is what is defining how the current is moving from the origin when the fault happened. I mean, what I'm trying to say is this term is trying to say how the DC component is affecting the total effective short circuit current. Okay. Okay. Now, what we need to do is, okay, we can say that this DC component is related with few things. One thing is time. Yes, of course, time is affecting the exponential, but also here we have a time constant, and that time constant depends on the ratio between the reactance and the resistance. Okay. Everything that I have been explaining is to make a very detailed introduction to say that the asymmetrical momentary current will be the asymmetrical factor at half a cycle multiplying the short circuit current that you will get from the Thevenin method. And for the interrupting current, you will use again the asymmetric factor, and you will use the Thevenin current, but in this case you will use the time that is defining the operating regime of your circuit breaker. Okay. Well, let's move forward. And here we have the momentary asymmetrical maximum current, and here we have the instantaneous. Okay, what you need to understand is that the operating time for separating the contacts, this number here, it's coming from standardized values. As I said before, there are few standards defining those times, operating time. And here you can see I create a table, and this table is for 60 Hertz. Depending of the operating time, for instance, for 2 cycles, the starting of the contacts is 1.5 cycles. Okay, this number will be used when you go to these plots over here, and for instance we are saying 1.5, and depending on the RH ratio, you will have different asymmetry factors. Okay, the interesting thing that you must realize here is that there is a maximum possible for the asymmetry factor. Okay. Again, what you need to understand, this curve over here, they are created based on the expression, on the relationship defining the ratio between reactance and resistance. Okay. Okay, simplify method here. Simplify method without the use of the curve, because some of my students say, okay, this is a graphical method, it could be a bit messy. Okay, using a simplified version of without using the graphic, we can say that this is the maximum momentary current, that is the maximum asymmetrical current that the circuit breaker must withstand, and this is 1.6 times the current that you will get from Thevenin. And for the momentary, for the interrupting current, what you need to do is use the Thevenin current multiplied by a factor coming from the table. And here you can see the table. The table is, for instance, for 2 cycles, you can use 1.2. And if your circuit breaker is 2 cycles, that means that the maximum asymmetrical interrupting current will be 1.4 times the Thevenin current. Okay, this table is quite helpful. However, again, it's very important that if you are using an application at the field, and you understand and you know the model of the circuit breaker, and you can go to the manufacturer and get a documentation and use the proper documentation for those things. Okay. Finally, I would like to close this with a short discussion. We need to be careful about the ratio between reactance and resistance. Okay. Reactance and resistance ratio is quite tricky depending on the location of the inside the power system, depending of the capacity of the components. You will have different reactance resistance ratio. Okay, you must be careful with this when you are calculating asymmetrical aspects of the short circuit currents. Okay. Well, we are finishing here. Thank you very much for this class. We presented a general overview about power system states and control actions in order to move from emergency conditions um, to normal conditions. I explained a bit, a very brief explanation about the cause of different abnormalities inside power systems, and I present the definition of short circuits and also classifications and possible cause and consequence. It was very important that I run an explanation about dynamic behavior of RL system, but also that explanation was the introduction for short circuits, three-phase short circuits in synchronous machines. Then I run an introduction about the methods used for calculating three-phase short circuits, the EMF method and the Thevenin methods, and then a very brief and not manufacturer-specific introduction of circuit breaker specifications. Okay. Again, I would like to suggest that you have a proper reading. If you are following my classes, you must realize that I make so many comments related with some books. One of them is Stevenson. You can have a reading on chapter number 8 at Stevenson. Also, they are very beautiful books like The Glover and Overby, Guidi, and also PM Anderson, okay, Paul Anderson, okay. Well, this is everything for the class today. I hope you enjoyed this class related with short circuit analysis, specifically symmetrical faults. Thank you very much for having me. Thank you.